Good afternoon.
Good afternoon.
All right, so let's see. Okay, so St. John's, your camera is way whack. And Mogyan, I see you're working on yours, so that's good. That's good.
Is it better now?
It's a little better. It still needs to go over to my left a little bit. You're right. Oh, other way. A little bit more. There you go. That's better. Okay. All right. So it looks like we're missing David. I think you
No,
told
Joey is gone today.
Joey's gone. Okay. All right.
Never mind, he's here.
Oh, wonderful. Okay, so yesterday was a little bit crazy with the snow day. Let's see, you guys and Mogyan. I think Miss Townsend told me you had a snow day. Winslow,
Yeah.
you guys didn't though, right?
No, we had a delayed start, but we didn't get a snow day.
Okay, so you kind of had my class off then, right?
Yeah.
So that's all right. How about in St. John's? What did you guys have going on yesterday?
Nothing, no change. It didn't really snow much here.
Really? Wow, that's crazy. Well, anyway, we definitely it was pretty dangerous out there in Joseph City. Somebody said it was and those of you that have your own cars, you'll appreciate this. They said it was a full coverage day. If you just had liability, stay off the road. So anyway, hopefully you understand what that means. But anyway, okay. So what that meant is that I really didn't know when to do the quizzes because we've changed around. Although Mogyan, I realized I should have just set up your quizzes for today at 10 because that's when you usually have had it. But I didn't actually get to my computer until after 10, and that's when because I teach at Holbrook first. So then by the time I got there, and I wasn't even able to get to my laptop yesterday because MPC was closed. So so I assume you guys didn't take the quizzes, Mogyan?
No, we went on and it wasn't even like an option to go take it, so we didn't.
Right. So at 10. So do you want them for tomorrow at 10 or another time?
Yeah, that works.
Okay. All right. How about the rest of you? Were you able to?
Is it just 7.5?
7.5 and 7.6.
Like Trig? That's right.
What?
I didn't have, there was like a minute left, so I didn't even start my second attempt for 7.6.
Okay, that's cool.
So could I do my second attempt for 7.6 tomorrow at the same time, 1:50?
Sure. Sure.
I also didn't take the second attempt to 7.6. Can you just send that to me after class?
You want yours after class today?
Yes.
Can
Okay,
we
so
go-
so David after class and Aiden tomorrow.
Yeah.
I have it.
Okay. All right.
And then we can do ours tomorrow after class.
Tomorrow after class. Okay. All right. Okay. All right. Yeah, I appreciate that. We'll just doing the best we can. So, yeah. So just know that if we ever have crazy disruptions in the schedule, just know we'll work it out. Okay. Don't over stress or over panic or whatever. Just know that we'll figure it out. Okay. All right. Well, all right. Well, so today then what we're working on is 7-7, and then we'll probably go into 7-8, just depending on how things go. So we're on the very last problem on the front side of 7-7. So if you want to go there, and we're going to go over that problem. Okay. Okay, so this problem was to do cosh squared, the integral of cosh squared. So the deal on this one is we really didn't have any of the hyperbolic trig functions where you had a power to it, okay? And so really the only thing that you could have done on this one, at least that I know, well, there's two things you could have done. Using the formula for the power reducing formula. So that the cosh squared x is cosh 2x plus 1 all over 2. Now, when you do the power reducing formula, actually you do that with the regular trig functions too, is typically it makes it so that you can integrate. Because you can integrate cosine 2x, or, easier than you can cosine squared. So same thing with cosh. So you pull the 1/2 out front, and then you have the integral of cosh 2x plus 1 dx. So then what's the integral of cosh from your formulas?
Sine HU plus C. I don't know how to say it.
And so you say it sinh. Sinh is with the hyperbolic sign. Okay? So the sinh of 2x. And then when you're doing the derivative, you multiply by the chain, you multiply by the 2. When you're doing the antiderivative, you divide by the 2. So you have 1/2 sinh 2x divided by 2. And then the integral of 1 is just x. And now you're going to plug in the 1 and the 0. And so that gives you 1/2 the hyperbolic sign of 2 times 1 over 2 minus the sinh of 0 over 2 plus 0. Okay, so did anybody figure out how to put these in the calculator? See, because in this problem, you actually have to use the calculator at some point, because I didn't get, like we have the unit circle with all the values on it. We didn't do one for the unit hyperbola. So like I don't assume that the hyperbolic sign of 2 or 0 or any of these. I don't expect you to know what those values are. So you have to put those in the calculator. Okay? So let's talk about how to do that. All right? Okay. All right. Okay. So here's the idea, is that there's no key for the hyperbolic sign or any of them. Okay. So what you have to do is go into the catalog of functions. And so it's listed there. So the hyperbolic sign, or the sinh, you just go to second catalog, and then you have all the functions that your calculator does alphabetically. Now you can scroll there for a long time, but what we can at least do is jump to the s's. And so to do that, you look for the alpha keys S. Under the alpha keys is the same as LN. So when you press that, you jump to the S's. Okay? Then you use the down button. And there's sine, inverse sine. Well, going too fast. Okay, here we go. And then the hyperbolic sign right there. And so here we want the hyperbolic sign of 2. So you could say the hyperbolic sign of 2. And so then you get that and plug in that value. Or you could actually plug in the whole thing at once and just work it all out. Okay, but you go into catalog and then the hyperbolic sign or the cinch. Plug in those values. So let's see, to do it again, if I do second entry and then I change the 2 to a 0, I can get the other value easier than going through that catalog. And so you get this is 0. So this whole second thing is going to turn out to be 0. Okay. Now, it's good to practice that a little bit and going through the catalog, but doing the power reduction formulas. Okay, but remember that whenever you have a definite integral, then you can always plug in the integral from the very beginning and get the decimal value. Okay, and so that's actually why I give you a lot of these definite integrals, is so that you can check with the calculator just to make sure that you're getting them right. But I would definitely practice doing them by hand if you can, and then plug it in and then check it with the calculator just to make sure that you're going through the correct steps. Okay? So on this, the final answer is 1.407. So if you haven't put that in your calculator yet, definitely write that answer down just to make sure that you can put it in okay. All right. Any questions? Okay. Okay. Now, let's see. I thought this had a blank to it. Okay. I guess, let's see, did we... Okay, so in this one, we have a hyperbolic function, trig function, mixed with e to the x. So whenever we have these mixed, then what you typically want to do is rewrite your hyperbolic function so that it's in terms of e to the x. So those 6 basic formulas that you wrote down at the beginning of 7.7, it says the 6 basic hyperbolic functions are where we listed all of them in terms of e to the x. So you just rewrite whichever formula in terms of e to the x. Okay, now, so let's make sure you're comfortable with the algebra here. Okay. So here, like, we can cancel the 2 with the 4. But then when we multiply e to the x times e to the x, remember you add the exponents when you multiply. So that's going to become e to the 2x. And then e to the x times e to the negative x, when we add the exponents, you get e to the 0, which is 1. Okay? So when I distribute the 2, the 4 divided by 2, times that, we just end up with 2. because this ends up is like 2 times 1. Okay. All right, now now that we've simplified, to do the integral, remember the idea of the integral of e to the u du is e to the u. So when I have, if I'm just trying to integrate this, I say, well, if I let u be 2x, du is 2 dx, then I end up with that this is e to the u, and then the 2 dx is the du. And so this integral is just going to be e to the 2x. And then the integral of 2 is going to be 2x. And so now when I substitute in and subtract, e to the 2 times natural log of 2, I'm going to write it as natural log of 2 times 2 so that the e and the natural log will cancel. Minus 2 natural log of 2. Minus, then I plug in 0 and I get e to the 2 times 0 minus 2 times 0. Okay, so this will simplify just to 2 squared, which is 4, minus 2 natural log of 2. E to the 0 is 1, 2 times 0 is 0. So then when I simplify, my final answer here is going to be 3 minus 2 natural log of 2. That's the exact answer, and then we have the decimal. Okay, so definitely a few algebra tricks there as far as simplifying the e and the ln or whatever, but really to start us off, is where we take the hyperbolic function and write it in terms of the e to the x. All right, so any questions before I have you start yours? All right, so go ahead and do practice 1D. All right, so Aiden, when you've got it, or if you get stuck, let me know.
So for my final answer, I got 3 ln 3 plus 1 divided by 2.
Okay, now The ln3 is not going to be divided by 2. Let's see. Let's back up. Okay, did you get this e to the 2x divided by 2 plus x? Did you get that for your antiderivative?
Yeah.
Okay, so then so when we plug in, so we get e to the, so I'm plugging in natural log of 3 for x. So e to the natural log of 3 raised to the second over 2 plus natural log of 3 minus, then you plug in 0, so e to the 0 over 2 plus 0. So, so e to the natural log of 3, the 3 will come down, so you get 3 squared is 9 over 2 plus natural log of 3. And then e to the first, or e to the 0 is 1, so you get 1/2 minus 0, so just minus 1/2. So then here you have 9/2 minus 1/2 would be 8/2, which is 4 plus natural log 3. Okay? So do you see where you messed up?
Yeah, just in the algebra.
Okay. All right. Any questions on that or on the calculus part? Getting to the integral. All right. Well, good. Now, over here, let's see. Okay. Well, I actually didn't do that one on the calculator. I just did it by hand. Okay. So next on your sheet here, there's some identities for the inverse hyperbolic functions. Now, so we've actually come to, so now we're doing inverse hyperbolic trig functions. Now, on these, the ones that I have numbered here, 1, 2, and 3, this is what you need to write down, okay, on your paper, are those identities. Now, what I've written down here in the different colors are the equivalent identities in using the regular trig functions to kind of help you understand how they're related. So the inverse sec of x is equal to the inverse cosh of 1 over x. Because remember, like secant and cosine are reciprocals. So the inverse secant of x is equal to the inverse cosine of 1 over x. So when you're doing the inverse trig functions, you do the reciprocal of the argument. Okay? Whereas when you're doing just the regular trig functions, like secant and cosine are reciprocals. But when you're doing the inverse trig functions, it's the arguments that are reciprocal. So that's a little tricky. The inverse cosec of x is equal to the inverse sec of 1 over x. Just like the inverse cosecant of x is the inverse sine of 1 over x. And then the inverse coth of x is equal to the inverse tan of 1 over x. Just like the inverse cotangent of x is equal to the inverse tangent of 1 over x. All right. All right. Well, let's go on to the next set of formulas, and these are all in your book, but and so I'm not going to spend as much time on this page because it is in your book, and there's really nothing special I'm adding to this. But this tells you how to get the derivative of the inverse hyperbolic functions. Okay, so the derivative of sec inverse is 1 over the square root of 1 plus u squared du dx. And so you just figure out what the u is and then apply the formula. And so it's not very difficult when you have all of the formulas there in front of you. But that's what we're going to be, we'll practice on a little bit, is using those formula for the derivatives. Okay? So, now, I do want to tell a little story here at this point, so you can maybe write down some of them. Years ago, well, some of you might be have a class with Kobe Corporate at Holbrook. I know Kobe knows you guys in St. John's and you ladies in Mogollon. I can't remember if do you guys at Winslow, do you guys ever team up with Holbrook on these town classes?
No, not usually.
Yeah, so I'm not sure, you might not know him, but anyway, his older brother I taught and several years ago, and he's actually went on to become like a corporate lawyer and probably making more money than me in like 2 years or something. But anyway, so but he had been in my class his junior year. He took Calc 1 and Calc 2 his junior year, and so then his senior year he was like my aide, my teacher aide. So I just remember the day I was teaching this lesson, I was so sick. I should have gone home, but it was the last period of the day. It was like this. I thought I can tough it out one more period. And the school also had it was like $1,000 bonus if you had perfect attendance. And so it was in February, and I'd had perfect attendance up to that point. I thought, I'm not going to go home for one period. Anyway, but I couldn't hardly even keep my head up. So Kobe's older brother, Corey is his name. Corey comes in the door, and I'm like, almost jokingly said, Corey, is there any way you could teach the lesson today? And then just saying the lesson, I actually laughed out loud because I thought, this sounds insane. I'm like, could you teach about finding the derivative and integral of inverse hyperbolic trigonometric functions? I mean, it's a mouthful to even say. And anyway, so he just gets up there and just teaches the lesson with no preparation. And I thought to myself, there's probably, I'm not even sure that any of the other math teachers in the math department could have done that. And so anyway, so you never know. You never know what you're able to do. So this is just applying the formulas. It's not like I was making him memorize anything. But so if we want the derivative of inverse cosh of 5x, okay? So then you say, well, I'm going to let the u be whatever the argument is, okay, the 5x. So then du dx is 5. So then when you apply it to the formula, it's the derivative is 1 over u squared minus 1 times the derivative, times du dx, times 5. So the final answer here would be 5 over 25x squared minus 1. See, that's compared to some of the other stuff we've done, applying these formulas really isn't bad. It just looks and sounds awful when you're trying to explain to people what you're doing. All right, so go ahead and try practice 2. See if you can apply those formulas. All right, so David, when you've got it.
Is it 4 over the radical of 16x squared plus 1? Or 1 plus?
Yeah, and since it is plus, it doesn't matter which order you have it. So good job. Any questions on that? All right, great job. All right, so the next one, it says integrals leading to inverse hyperbolic functions. So kind of coming back the other way, you have these, and we're, so like if you have the integral of the derivative du over the square root of a squared plus u squared, then that gives you the inverse, the hyperbolic sinh of u over a plus c. And so on these, it's a matter of recognizing these formulas, recognizing the pattern, okay? Now, the tricky ones here is actually number 3, because I always have students that ask me, like, well, how do you know if u squared is less than a squared, or if a squared or if u squared is greater than a squared? How do you know? Well, if you're not given limits of integration, you don't know. And so you just pick one. And so it works either way. If you're given limits of integration, then you can, sometimes figure out, okay, if I'm plugging in 1 for u and a is 3, then u squared would be less than a squared, and so you'd use this top one. Otherwise, you use the bottom one. But that's really the only real tricky thing there. And like I say, typically, you don't have to worry about it unless you have limits of integration. And you just don't know. Okay, so I'm going to let you copy those in the book, from the book, on the paper. So now I'm going to show you how we're going to use it. Okay, so what we want is typically a squared and u squared in the denominator for these. So you think, well, what squared would give me 4x squared? That would be 2x. So let that be your u. And then even though 3 isn't a perfect square, it is radical 3 squared. So typically what I want is to have the constant squared be that number. So let a be radical 3. And then u is 2x. And then you need to write down what du is. So the derivative of 2 is 2. The derivative of 2x is 2 dx. Well, so it turns out that 2 dx is exactly what I have there. So when I do the u substitution, see, this is going to give me du, and this is going to give me the square root of a squared plus u squared. And so then the answer is going to be the inverse sinh of u over a plus c. And so now I say, okay, so this is radical 3 is a, u is 2x, so it's going to be the inverse sinh of 2x over radical 3. And I don't have to do the plus c because I have limits of integration, 0 and 1. So now I plug in the 1, and then I plug in the 0. So I have the inverse sinh of 2 over radical 3 minus the inverse sinh of 0. And so this is the case where the part where I don't expect you to have any of this memorized. So you put this into your calculator here or at the very beginning. But here I did the inverse sinh of 2 divided by radical 3 minus the inverse sinh of 0 and got 0.987. Okay. All right, go ahead and try practice 3 for me. All right, so Jordan, when you've got it.
Question. So on the board up here, you have written that it's a 2 and a 1/2. Is that changing the 3 or what?
No. What it is, I'm giving you a little hint that, see, you don't need the 3. So you can move that out front. Okay? But see, what squared gives you 4x squared?
2x squared.
2x. And then what's the derivative of 2x?
2.
2 dx. So you're going to need a 2. And so when you write a 2 there, then you got to put a 1/2 out front.
Okay, I just saw that and I was really confused on what it was.
No, I'm not changing the problem there. I'm trying to just give you a little hint with the constants a little bit. So
Okay, thanks.
sometimes when the teachers try to help you, they just make it more confusing. Sorry.
Okay.
I got 1/6 hyperbolic inverse tangent, and then of 2x divided by 3, and then close the parentheses, plus c.
Okay. Couple of things. So the a is not 3, but radical 3. Because it's a squared. Okay? And then when you bring the 3 in front, and then you have to multiply by a half, then it becomes 3/2 in front. And then the other, and then everything else you have right, except that the a here is going to be radical 3. So it's 1 over radical 3. And you could add those together. But the argument here is going to be 2x over radical 3, not 2x over 3. Okay? So you got to watch the A.
Why did you use hyperbolic cotangent instead of hyperbolic tangent?
So let's see. You don't have. You don't really know which one to use because you don't know the A or the U. You don't know which one's bigger. Because see, we don't know what x is here. So without limits of integration, we don't know. So you could use either one. Okay?
Mr. Strong,
Yes.
I have a dentist appointment right now.
Okay.
I'll get the
Okay.
notes from someone though.
Okay, so let's see, wait. Okay. And so you're doing your quiz tomorrow after class?
No, tomorrow 150 to 250.
Oh, 150, 230. Okay, got it. Okay. All right, so the last little part here is actually because some calculators don't have inverse hyperbolic functions, and some professors actually prefer the answers to be put in terms of logarithms. So there's a series of formulas where you can rewrite the inverse hyperbolic functions as logarithms. Okay. Now, I kind of like these. I mean, it looks pretty ugly, but it's actually not that bad. The thing that bothers me about this book is that they throw these formulas in the middle of the homework problems. And so, in matter of fact, in the last edition of the book, they would ask the question and then they didn't have the formulas till the next page. And so if you didn't turn the page, there was no way to do the problem. And I hated that. The other thing is on Kosh, if in some of the editions in your book, when they have these listed on page 431, on some of them, they have the formula for Kosh wrong. And so that's why I highlighted or put this part in red, -1, because it might be accurate in your book, but some books it's wrong. And so I would hate for you to miss a problem because you're correctly copying the formula from the book. So this is just, you take your different hyperbolic and inverse hyperbolic functions, and then you rewrite them as logarithms. Let's see, there's actually 6 of them. So for all 6 of them. Now, they look pretty awful, but you're going to see as we actually do one that it's not going to be so bad. Okay? So, again, I'm gonna let you finish copying them down after class. I'm going to just do one here. So if I do the inverse cosh of 13/5, see, I'm using the second one. I want to do that one because of the typo. So whatever the x is, whatever the argument is here, you plug it in for x into the formula. So it's going to be the natural log of 13/5 plus the square root of 13/5 squared minus 1. So you work on the radical. 13/5 squared is 169/25 minus, rewrite 1 as 25/25. So you can combine those and you get 144/25. And now both of those are actually perfect squares. So the square root of that is 12/5. And then 13/5 plus 12/5 is 25/5. So the natural log of 5 is your final answer. And so that's actually pretty slick. That's a nice way of writing your final answer as a natural log. And instead of, and people have a better idea of what that means than an inverse hyperbolic cosine. Okay? All right, so go ahead and try that last one on the page practice 4. I'll go back to the formula page in case you didn't get that. All right, Joey, I pick you.
Okay, I got the natural log of 1.354. I didn't get it into fraction form. Sorry.
That's all right. I mean, and this one, because 185 is not a perfect square, it's not going to work out really well. So the natural log of 1.354 is great, and then you can actually put that in your calculator. If you left it in the fraction form, it would be that. So really, any of these are fine there at the end. Does anyone have any questions plugging it in? Or simplifying? Okay, well, that's it for today. So we'll start off with 7.8 tomorrow. Remember, Monday, we're going to try to just do a Moodle day. So we're not going to have class. We're going to just have like the 7-7 quiz open all day or something like that. So you can do it at home. And we'll talk more about that tomorrow. Okay? All right. So we'll see you. You guys have a great one.